So hello there. My name's Ishan. I am sort of just wanted to go through the 2024 chemistry NHT exam. So it recently came out. I believe it was done on 22nd May, so I'm a bit late to the party. But I thought I'd just sort of have a quick look at the exam. This is my first time looking at it. In this video, I'll be going through the multiple choice. However, in another video, I'll be going through the short answer. But yeah, 30 MCQ shouldn't take us too long. But yeah, let's have a go at it. I'm going to be using the highlighter, sort of just the Microsoft Edge functions on the laptop available. Okay, so which one of the following, okay, correctly compares fuel cells and galvanic cells? So yeah, this is a pretty standard question. Galvanic cells use a stored supply of reactants. Fuel cells use a continuous supply of reactants. Yeah, so this is one of the main differentiating features that sort of differentiate fuel cells from galvanic cells, right? The fact that fuel cells sort of have that continuous flow of reactants as opposed to galvanic cells, which have a stored supply, okay? So that leads me to have the answer be A. However, it's very important that we look at the other options as well. So galvanic cells, so obviously B is just the options of A, but switched around. Galvanic cells convert electrical energy into chemical energy. Yeah, so that's actually describing an electrolytic cell. Okay, and we can see that the same thing's been written here. So that's why we can sort of cross out B, C, and D. Okay. Which value can be calculated with data from a calorimeter? So a calorimeter, as we know, it's sort of an insulated way of, finding out what the heat value is, of a certain substance, right? So in school, you guys might have done, like, burning a chip, for example, or burning some sort of food, and finding out what the heat value of that is, right? Which value can be calculated? So the standard electrode potential of a redox reaction, not really. We use a voltmeter for that. The equilibrium constant of a chemical reaction, again, not really, right? So when a chemical reaction reaches equilibrium, we use the concentrations of each of those species, and then we calculate the equilibrium constant from that. The calibration factor of a chemical reaction. So again, yes, we can. We can sort of uh, you know, calculate that. However, I think that's not sort of the end value that we're looking at. I think the end value that we're actually looking at is the enthalpy change. Okay, so the enthalpy change of a chemical reaction. However, I do believe C could be right as well. Um, so it's a bit of a weird question because I believe that, yeah, the end value that we're trying to sort of calculate from a calorimeter is the enthalpy change, right? We're trying to see how much heat has been absorbed or released from a chemical reaction. However, I do believe that we can also calculate what the calibration factor is. So it is a bit of a hard one. I would sort of lean towards D though, right? Because calibration factor is sort of the middle ground. What is the end value that we're trying to actually calculate? It's the enthalpy change. However, I will have a look at that. Okay. Which one of the following statements is true of a scientific poster? The discussion section should identify outliers in the results. Yeah, so that's pretty true, right? So the discussion should really identify what the outliers in the results were, explain why they were, and sort of how can we go about mitigating them or making sure that they do not exist the next time we do the experiment, right? The introduction section should present the experimental procedures. Not really. I guess it can sort of provide an introduction or like can provide the introductory concepts, but should not be presenting the experimental procedures, right? So that's more later down the road. The conclusion section should explain background chemical concepts. That's more the introduction, like I was talking about. And the results section should compare results with theoretical expectations. Yeah, so it could. However, yeah, I guess this is more the job of the discussion, right? So the discussion is more concerned with, I guess, really comparing those results with the theoretical expectations, okay? Which is why I'm leaning towards A, okay? Um, cool. Catalysts increase the potential energy of the reactants in a reaction. So they don't actually affect the energy of the reactants of the products. All they do is decrease the activation energy, which is why it leads to me to go to C. B, shift the equilibrium position of the reaction. Not really, again. It could affect how quickly it gets to the equilibrium or how it reaches equilibrium. But yeah, it doesn't actually shift the equilibrium position. And D, stabilize the products of the reaction. Again, it doesn't really do that. Okay. Collision theory, all right, applies only to gases at standard temperature pressure. Not really. Okay, it can apply to other things such as reactions that involve aqueous substances. All right, explains why particles with a small surface area have a greater rate of reaction. Yeah, so it's not just small surface area, it can also be, so it's not small surface area, it's actually greater surface area, okay? So when, we have substances with a greater surface area, they have a greater rate of reaction, so that's wrong. Asserts that a reaction only occurs if reactive molecules collide with a kinetic energy at least equal to the activation energy, so that is right? And a reaction can only occur if that occurs. Predicts that increasing the temperature increases the proportion of reactant particles that collide in correct orientation. So yeah, I would normally say that this is correct. However, I won't say that increasing the temperature actually impacts the way in which reacting particles sort of collide in correct orientation, right? So it's actually not affecting the correct orientation, right? So I would go for C because yes, increasing the temperature does increase the proportion of reactant particles um, that have fruitful collisions, right? But it doesn't really affect the ones that collide with correct orientation, which is why it leads me to go C. I think the wording of some of these questions could be improved slightly, but yeah, it's not too bad so far. So yeah, two substances are added to a test tube. Uh, when the reactants are mixed, the test tube becomes colder. Which one of the following is the correct description of the chemical reaction that occurs in the test tube? So yeah, this would definitely be an endothermic reaction just because if the test tube is becoming colder, it means that it's actually drawing heat from the surroundings and it's absorbing it, right? So definitely be endothermic, right? And if you can imagine that if these two are the substances that we're adding, and then we're adding energy, right? Because it's an endothermic reaction and it's going to go and form Z, it means that the energy is basically being converted into a mass, right? So it's endothermic and it's yes. So yes, energy is being converted into mass from my sort of um, from my understanding. Okay. Um, what is the pressure of 3 moles of gas in a 60-liter container at 127? It's pretty easy. We're going to be using PV equals to nRT, which is the universal gas equation. All right, so P equals to nRT over V. All right, so it's just going to be 3 times 8.31 times 127 plus 273. All right, so the only hard part about this, I would say, is just making sure that we convert the degrees Celsius into Kelvin. So remember, Kelvin is just degrees Celsius plus 273. Okay, and then we just grab our calculator out. All right, and it's 166.2, right? So it's most likely going to be C. Faraday's first law of electrolysis states that the amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. Yeah, so that's what sort of that linear graph comes from, right? So yeah, that's what that is. Which one of the following variables should be measured in an electrolytic cell to test Faraday's first law of electrolysis? Yeah, so current through the circuit, not really. Change in electrode volume would probably be the best, probably be the best answer for that, just because it's sort of testing, well, how does the electrode volume change, right? Because when we are dealing with an electrolytic cell, we've got an anode and a cathode, right? And say, for example, we've got X plus uh, you know, e to give x and then y plus 1. So let's say, for example, where we're dealing with these two equations, right? X is probably going to be converting into x plus, and then y plus is being converted into y because obviously cathode reduction and an oxidation. Obviously, the the amount of moles that are being lost at the anode should be proportional to the ones that are cathode, right? And so because of that, the electron volume would be being changed, right? So that is what we are basically testing. Hopefully that makes sense. It will be a change in electron volume. When 5 grams of ethanol undergoes complete combustion in air, the mass of carbon dioxide gas produced is, okay, so this is pretty easy, okay? What you need to do is you basically need to find out the moles of ethanol, okay, which is just 5 divided by, I think it's 46 from my understanding. All right, 5 divided by 46, it's 0.11. Okay, now we need to find out the moles of CO2. Now, instead of me going ahead and writing out the entire equation, I can basically see that because there's only 2 carbons in the ethanol compound, it means that there's only going to be 2 moles of carbon dioxide as well, right? That's the only amount that's possible, if that makes sense, right? So it'll just be 2 times 0.11, which is 0.22 moles, and then you just times that by its molar mass, so it's 0.22 times, what is it, 44 times 0.22, which is about 9.68. So it leads me to believe that it is C. Not too bad. Yeah, cool. Consider the following statements. An energy profile diagram represents the enthalpy changes of an exothermic and endothermic reaction. Yep, so that's true, right? That is basically what an energy profile diagram is there for. It basically represents the enthalpy changes of an exothermic and an endothermic reaction. The only thing I'm a bit concerned about is that it doesn't show the enthalpy changes of an exothermic and endothermic reaction at the same time. It's more, it should be, I'm not sure if I'm looking too deep into it, but ideally it should have said or, but I'm still leaning towards this being right. Okay. Exothermic reactions have a higher activation energy barrier than endothermic reactions. Yeah, so this is obviously wrong. You know, regardless of whether you're absorbing heat or releasing heat, it has no sort of relation to how high your activation energy barrier can be. So I'm sort of leaning towards one only. However, it could also be neither one or two. Okay. I might put this as a D as well because it says it represents the enthalpy changes of an exothermic and an endothermic reaction. Okay. However, obviously, and one energy profile diagram can only show the changes in one at a time. You know. Anyway. The solution of 0.125 methylamine reacts with 50 mils of 0.2 molar hydrochloric acid in a titration. What volume of CH5N solution is required to fully react with the HCl solution? I'd say, yeah, it's a pretty simple question, okay? We can see that this is a monoprotic acid. What do I mean by that? It means they only donate one hydrogen ion, okay? So it's most likely going to be, and this is only one amine, right? So it means that it's only going to accept one H plus anyway. Why is this significant? It means that the ratio between CH5N and HCl is 1:1. Okay, so it's going to be NCV. Okay, CH5N. Okay, NCV. We can see what 0.05, 0.2. All right, and the moles of HCl and CH5N are going to be the same. So it'll just be N of HCl 0.2 times 0.05. And that is 0.01. All right. Then the moles of CH5N are going to be the exact same, so 0.01. And it's just asking for the volume, right? And the volume is going to be, right, N over C. So 0.01 over 0.125. And hopefully that gives us a nice answer of 0.08 liters. All right. Which one of the following statements regarding fuel cells is correct? The state of the electrolyte can be aqueous, liquid, or solid. This is actually right. So solid, because it can be things such as, ceramic oxide. If you guys have done past questions, you would have seen that, yeah, a lot of the times the electrolyte has been like, ceramics and stuff, for example, O2 minus. It can be liquids and obviously can be aqueous, right? Another one that we've looked at is like a polymer electrolyte membrane. Which I believe is solid. I'm not do not quote me on that. But yeah, let's have a go. Let's have a look at the other ones. So the porous electrodes decrease the contact area for the reactants. It actually increases it. During operation, gases move through the membrane. Yeah, so the membrane, not really. Okay, so the membrane exists in the first place to basically make sure that only the ions, for example, in an acidic fuel cell, only the H plus ions actually move through the membrane. All right. And during operation, the cell voltage decreases because the reactants are used up. Yeah, so one of the differentiating factors of fuel cells is the fact that, the reactants are at a constant flow rate, right? That they're never going to be used up, right? If it was a galvanic cell, it'd be a different story. All right, so the three unknown organic substances X, Y, Z were tested for their flash points. X had the highest flash point, whereas Z had the lowest flash point. Consider the boiling points and viscosities of X, Y, and Z. Which one of the following would show the same trend as the flash point? So yeah, what basically X, Y, and Z represent, okay? Well, basically what flash point represents is how strong the intermolecular forces are, right? And so what we're seeing here is it's X, Y, and Z, right? And basically what we can see is that if X has the highest flashpoint, it means that it's the most resistant to its intermolecular forces being broken. So if we were to look at it, it would basically mean that X has the strongest intermolecular forces and Z has the weakest intermolecular forces. And what you'll find is that viscosity and boiling point actually follow a similar trend as flashpoint, where it has to do with the strength of intermolecular forces, right? So if it were to show the same trend, it would be both boiling point and viscosity, right? Because viscosity is to do with the resistance to flow, and it'd be more resistant to flow if the intermolecular forces of a substance are stronger and therefore more adhered to each other. I know that was a really bad explanation, but hopefully that makes sense. Which one of the following statements is correct for both electrolytic cells and galvanic cells? So the anode is negative, so only in galvanic cells is it negative, in electrolytic cells it's positive. The half cells must be separated. So yeah, again, only in galvanic cells, not in electrolytic cells. But the reason why it must be separated in galvanic cells is because we're harvesting the electricity, right? Whereas in electrolytic cells, we really don't need to do that anymore, right? Because yeah, with the separation of half cells, what we are creating, right, is this sort of external circuit in which we can sort of harvest this electricity, okay? The overall chemical reaction is exothermic. Yeah, so not really. I guess in this one, because we're converting C to E, this could be considered exothermic. However, in electrolytic cells, converting E to C, right? Which could be considered endothermic, so it would not be right. Electrons move from the anode to the cathode. Yeah, so this makes sense, right? Because the anode, regardless of whether it is an electrolytic cell or a galvanic cell, will always be the site of oxidation. And for the cathode, it'll always be the site of reduction. Right. And that makes sense, right? Because you're letting go of electrons at the side of oxidation, so at the anode, and then you're gaining electrons at the cathode, right? Which means, yeah, we're sort of creating the circuit, and that's why D is the right answer. Cool. Let's keep going. Um, I think, yeah, a sample of gas occupies a volume of 10 liter, 25 degrees Celsius to atmosphere. The temperature of the gas is increased to 50 degrees Celsius at constant temperature. Which one of the following is the closest to the new gas volume after the temperature increases? Okay, this is not too bad. Again, we would just go 10 divided by 25 equals to 50 x. So it's just a ratio. So it's just going to be 20 liters. Okay, I think this is to do with Charles's law. Um, I didn't, yeah, I don't, it's not tested as much. So it was pretty surprising to see this. But yeah, the whole idea behind Charles's law is it's V1 over T1 equals to V2 over T2. So that is Charles's law. And so then, yeah, basically we can see that the temperature is doubled, so the volume would also double. All right, halfway there. When a fat molecule is hydrolyzed, 3, what is formed? So yeah, a fat molecule is basically, I think they're referring to a triglyceride here. And a triglyceride is made up of 3 fatty acids. There's 3 fatty FA and 1 glycerol, right? So it's saying 3. So it'd probably be here, fatty acids. So it'd probably be carboxyl groups, right? Because 3 ester groups are being broken. 3 water molecules are being used, so hydrolyzed, so it's using water molecules, and only 1 glycerol molecule is formed. What is the value of the calibration factor for the bomb calorimeter in joules per degree Celsius? This sort of reminds me of the question that we had before. But yeah, anyway, this is not too bad. So yeah, again, you just need to remember the formula, which is VIT over your temperature change, right? And that's yeah, pretty much the formula. So it'll be 4.5 times 2. Now you don't actually times it by 2 minutes, you times it by seconds, right? So it's 2 times 60 over 1.5. So yeah, generally so far um I found the um I found this exam or these multiple choice questions to be relatively accessible. The only thing that I'm concerned with is some of the wording. Maybe I'm looking a bit too deep into it, but yeah, some of the wording is can be a bit confusing. Um, but yeah, that's okay, of course. So here HPLC is used to separate a mixture containing methyl ethanoate, propanoic acid, and butanol. This technique uses a polar stationary phase and a non-polar mobile phase to achieve separation. Which one of the following describes the state of the mobile phase and lists the three molecules in order of retention time from shortest to longest? The state of mobile phase. So it's most likely that the mobile phase would be probably liquid, just because, yeah, I mean, it's mobile. I've never really seen a mobile phase within HPLC that is gas, and it's also called high performance liquid chromatography. Okay, so that makes our job slightly easier. We can see that at the end, it's either butanol or propanoic acid that has the highest retention time. Now, because it's a polar stationary phase, the molecule that has the highest retention time would be the one that is most polar. And it is pretty clear to see that propanoic acid is much more polar than butanol. Several reasons for this. First of all, this only has 3 carbons. This has 4 carbons. Okay, so I guess butanol has a longer sort of carbon backbone chain, and therefore a greater proportion of it is non-polar as opposed to propanoic acid. And also, this is composed of CO and OH, whereas this is only composed of OH. So it sort of adds to its polarity. I know that was a bit of a weird thing, but yeah, it definitely means that yeah, propanoic acid is the most polar. This only has a carbonyl bond in it. This only has a hydroxyl in it, and the propanoic has both. Okay, which is why it is the most polar. Okay, that was not too hard at all. Okay, cool. Yeah. I think cool. Which one of the following options is correct? I think this is in relevance to HPLC. So the sample is vaporized before passing through the stationary phase. I think this is done in other chromatography techniques, but not necessarily HPLC. A calibration curve can be used to identify each component of the mixture. So this is talking about when we're identifying each component, that's a qualitative determination. When we are using a calibration curve, we're trying to do a quantitative determination. What we're trying to do is we're trying to find the concentration of each component within the sample, okay, which is why B is all right. Pressure is applied, okay, so yeah, in stylized images of the HPLC, you can see that there's a little bit of a pump that they use, right? Why is that pump used? Is because sometimes when the mobile phase is going over the very, tightly packed stationary phase, there's a bit of resistance there. So yeah, C is right. And a high retention time indicates that a component is highly attracted to the mobile phase. It's not the mobile phase, it's the stationary phase. All right, which is why I am led to believe that it is C. All right, 10 questions to go. Let's do this. All righty. Which one of the following shows the correct IUPAC name and type of alcohol for the molecule above? Cool. So we can see we just want to basically find out what the longest carbon chain is. I'm pretty sure it's just this stuff. Oh, it's not letting me. Okay. Um, it's the longest, so yeah, it's the longest carbon chain. And basically we can see that's 5 carbons, so pent, 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 that's fine. We can see that the alcohol is also on the 3rd carbon, which is also great. Okay, now it's also separated the alcohols into secondary or tertiary, but it's very easy to see that this would be a secondary alcohol. Okay, why is that? Because the carbon that's connected to the hydroxyl group is only connected to 2 carbons. Okay, if it was connected to a 3rd carbon, it'd become a tertiary, but it's only connected to 2 carbons, which makes it a secondary alcohol. So it's either between these and these. And then the last thing that we have to consider is this. It's on the, if we were to number it from top to bottom, it'd be on the 2nd carbon. So it'd be it would be 2-methyl pentanethriol. Okay. Which one of the following skeletal formulas represents the product of a condensation reaction between methanoic acid and ethylamine? For this one, I think it's best if we just sort of draw it out. Makes our life super easy. Okay, we want to get these 3 out, so that makes water, so it's what it's going to be looking like this. Like that. And then remember, right, in skeletal formulas, you don't want to have the C's there, so it's just going to look like that, then that, and then boom, boom. Okay, so we just need to find something that looks exactly like this, and it wouldn't take too long to see that D is the best answer for us. all right, if I've seen everything, right? So the reason why it's called a condensation reaction here, right, is because this water is being taken away to form this amide bond, okay? Amide bonds are very, very important, especially in this year's study design, okay? Cool. Cool. So basically, considering the following reaction, okay, this is negative, so it means that the energy is going to be, it's an exothermic reaction. Now, it's asking that it's initially at equilibrium, and then at time t1, the temperature of the reaction vessel increases, right? So which graph best shows how the rate of the forward reaction changes after t1? Cool. So this is not too bad. We just basically want to see how it changes. Now, theoretically speaking, if we were to look at equilibrium, if the temperature increases, right, what is LCP going to say? It's like, hey, I want to decrease temperature, right? So it's actually going to favor this side in which energy is not being produced, right? Because energy is on the right side, right? So back reaction is going to be favored, right? So what's basically going to happen, right, is we've got a normal equilibrium thing like this, okay? The new equilibrium position of like the new rate of both reactions will be slightly higher. So what it's going to be is this is going to be what the forward reaction looks like, and this is what the back reaction is going to look like, right? It's going to go up by a bit more, and then it's going to come down like this, right? So we just need to find something that looks similar to this, okay, to the orange one, and I think C sort of takes the win there, okay? Because we can see that the back reaction sort of takes the precedence. So the back reaction will sort of come down like that, okay? And eventually reach equilibrium, right? Because if we were to, increase the reaction, then the new reaction rate should be greater. Trehalose C12H22O11 is a molecule found in mushrooms. Its molar mass is 342 grams per mole. Almost all humans produce an enzyme in the small intestine called trehalase, which breaks down trehalose into smaller molecules. Okay, so guys, it's very easy to see, but you can see the ether bond, that glycosidic linkage between these two glucose molecules, I presume. So what I believe is happening is C6H12O6 plus C6H12O6, right, come together to form C12H22O11 plus H2O, right? So it's a condensation reaction, etc., etc. Which one of the following statements regarding tetrahalose is correct? The product of tetrahalose digestion can be hydrolyzed to form glycogen. So glycogen itself is a polysaccharide of glucose itself. So that would not be right, okay? We are breaking it down to form glucose. Eating tetrahalose causes an increase in blood glucose levels in most people. Yeah, so I could say that that is somewhat correct. Why? Because as I said here, right, this is a condensation reaction, but the reverse is also true, in which there's a hydrolysis equation. And yeah, as you can see, two glucose molecules are being formed. So yeah, it's likely that, yeah, it increases blood glucose levels. And digestion of tetrahalose produces two products that have a total molar mass of 324. So yeah, it says 342 above. So I think that's just a typo. Should say 342. But again, this is not going to be right, okay? Because what you are forgetting is water here. So each of these actually have a molar mass of 180. So it'd be 360 instead of 342. Okay, so it's only going to be 2. That is right. Okay, cool. Perfect. Alrighty, we're nearly there. The horizontal axis of an energy profile diagram is labeled time. So yeah, we never really want to label the horizontal axis of an energy profile diagram. The best you can do is maybe say reaction pathway, but yeah, we never really want to label it time, okay? Because the energy profile diagram gives no indication of time. The shape of the energy profile diagram is not changed if one reactant is in excess. Yeah, so that's right. If something's in excess, it doesn't affect the energy of the reactants themselves. That's something really, really important to understand. Again, energy profile diagram is only giving a an indication of not like the rate of reaction or like how much of each substance is being produced. It's simply giving an indication of how much energy is being absorbed, released from the starting to the finish. Okay, so that seems to be quite right. Energy profile diagram represents the average chemical energy of a reaction mixture. Again, not really. It's showing how much is absorbed or released, but it's not really giving any indication of an average chemical energy. And the energy profile diagram for a chemical reaction can be determined using a bomb calorimeter. This is a sneaky one, I think. I think not really, just because it's only giving us the delta H, right? But it's actually not giving us the starting energy or the finishing energy, right? So even if we know that the delta H is like 30 kilojoules per mole, for example, right? We don't know where to start or where to end, right? We do know the difference, but we don't know where the start or end is, okay? Which is why I believe B is the answer. A dipeptide is shown. The correct names for the two amino acid residues in this dipeptide are, so the dipeptide basically is connected by a CO and H amide bond, right? So it's going to be this. And basically what happens is this stuff is cut. It's cut here, right? So what we can see is we just want to find out where the R group is. So that's the carboxyl group, that's the NH group. So this is what our R group would look like. And then we just want to go down to the bottom. So CH2, CH2, COOH. Now we just want to go down to the bottom and we want to see where CH2, CH2, COOH is. CH2, CH2, COOH is, yeah, so glutamic acid, CH2, CH2, COOH. So it's glutamic acid, so let's go back to the top. Ideally, I would have looked at both, but that's okay for now. It's glutamic acid. And then we can see that I think this is the amine group. That's the carboxyl group. That's the H group. So this entire thing is our R group. Okay. So we're looking at CH2, CO, and H2. CH2, CO, and H2. And we can find it here. Okay, so it's asparaginine. Alrighty. It's not too bad, not too bad. So asparaginine, perfect. One molecule of chlorine gas reacts with one molecule of 2-methylbutane. Okay, so what does 2-methylbutane look like? Something like that. In the presence of UV light, the number of possible products that have an optical isomer is, so in order for something to have an optical isomer, it needs to have a chiral carbon in it. What's a chiral carbon? A carbon that's connected to 4 different functional groups, right? So each time we react with a molecule of chlorine gas, right, only one chlorine can replace a hydrogen, okay? So what I'm gonna do is I'm gonna basically, let's say for example, we add, all right, I'm gonna do it in another color. Let's say for example, we add a chlorine here, right? Can you see how it's actually not going to be it's actually not going to be uh, a chiral carbon that is generated, okay? Just because, okay, it's connected to a CH3 and a CH3 here, okay? So it's connected to the two of the same thing. So it's actually not going to be a chiral carbon, okay? However, let's say, for example, this goes back to being a H. It's a bit of a trial error, but not really. What if there is a chlorine here? Would that change anything? Well, yeah. We can now see that this will be a chiral carbon, okay? So that's one situation in which so far there'd be a chiral carbon because this carbon is connected to a CH3, it's connected to a chlorine, a hydrogen, and then this, all of that stuff. So that's a chiral carbon. So there's one there. Any other combinations? So yeah, we can't put a chlorine here because it's connected to 2 H's. We can put a chlorine there, but it's not going to result in an optical isomer. All right, same thing here and same thing there. So it's actually only one that results with, all right, the formation of an optical isomer. I know I sort of rushed that, but hopefully that makes sense. Yeah. Lithium ion cells are used in mobile phones. Which one of the following statements about lithium ion cells is correct? The extent of the reaction increases after each recharge. It actually decreases, okay? That's why, our computer batteries over time sort of die off, right? The quality of the recharges decreases. A high battery voltage indicates a high rate of reaction. Not really. So, and a high battery voltage indicates a high extent of reaction. Not really as well. So what we need to remember is that even if they give us two options that have the same, they're describing the same thing, it's not necessary that one of the two are correct. They could both be wrong, right? Because at the end of the day, what is a high battery voltage? It's just measuring this, like the the difference in electrode potentials. So it's more to do sort of with like, I guess, current, not necessarily the high extent of reaction or high rate of reaction. So it'd actually say that the answer is B. The battery current is affected by the surface area of the electrodes. I think that is actually a better way to look at it, right? Because I guess the greater surface area you have, the greater opportunity available for reaction, and therefore the greater the current. Okay. Alrighty, nearly there. Maxwell-Boltzmann distribution describes a particular sample of gas. The area under the Maxwell-Boltzmann distribution curve represents the total number of particles in the sample. I think that's just something that we need to know. Okay. Cool. Consider the methanol oxygen fuel cell and experimental galvanic cell. Both the fuel cell and experimental galvanic cell are NSLC and using acidic electrolyte. Experimental galvanic cell. Okay, so these are, I guess this is one half cell. This is the other half cell. Ideally, this is going to be the anode because it's getting oxidized. This is going to be the reduction. Okay. Okay, so this is going to be the plus cathode. This is going to be minus oxidation, right? And then obviously we know how a methanol oxygen fuel cell works anyways. So which one of the following is correct for every mole of CH3OH reacted? At the positive electrode, same amounts of water are produced in both cells. Okay, so at the positive electrode, so here, let's quickly have a go at balancing this equation. Right, so that's for a galvanic cell. Right, so I just use cohees there. I'm going to change the color here. And then this is the one for the fuel cell, right? The one that's the one that normally happens, right? The oxygen fuel cell at the cathode. So can you see how for the same amount of electrons being used up, there's actually a difference in the amount of water that's being produced? So this is actually wrong, right? This says 4, this says 2. At the negative electrode, the same amounts of greenhouse gases are produced in both cells. So yeah, I'd be inclined to say that this is correct, just because there's no difference. Since they both use an acidic electrode, there's no difference in the oxidation of methanol to form CO2 in the fuel cell and the galvanic cell, right? Because in the galvanic cell, it's getting oxidized to form CO2, and it's the same in the anode of a fuel cell. So I'm inclined to say this is right, but let's have a go at the other ones as well. At the negative electrode, the amount of greenhouse gases produced is lower in the experimental galvanic cell than in the fuel cell. So it's likely that it's actually going to be the same, okay? Just because, yeah, it's the same reaction. And at the positive electrode, the amount of water produced is lower in the experimental galvanic cell than in the fuel cell, so it's actually higher. So that's why I'm inclined to say that B, that is the one that is correct. But, yep, so hopefully that makes sense. All right, lastly, 5 peaks in the carbon-13 NMR spectrum of a pure amino acid is shown below. So there's five carbon environments. This is probably representing the COH. Yeah, so we can see that there's 5 carbon environments. So it might be slightly hard, but I'm hoping that only one of these have 5 carbon environments and the rest have 4 or 6. Just make my life slightly easy. But let's go through valine, proline, glutamic acid, and aspartic acid. So yeah, let's go down to the bottom. So valine, we can see that valine actually might have 5 carbons, but this CH3 and CH3 actually are part of the same carbon environment, right? Because it's connected to the same stuff. So it actually counts as one carbon environment, and there's 2, 3, 4. So there's actually only 4 carbon environments, which means we can cross out valine. All right. The other one was proline. So proline, there's 1, 2, 3, 4, 5. And yeah, none of these share the same environment. So there's 5 carbon environments there. That's fine. Then we had aspartic acid. What was aspartic? Yep, aspartic acid. Again, 1, 2, 3, 4. So there's only 4 carbon environments. So again, we can't have aspartic acid, and then glutamic acid 1, 2, 3, 4, 5. We can see that there's 5 carbon environments. Okay, so we can see that the battle is between glutamic acid and proline. But what I found interesting is that glutamic acid actually has two carboxyl groups, right? And they're non-equivalent, as you can sort of tell, right? They're part of a different environment. So what I was expecting in the CNMR, if it was to be glutamic acid, is I would not only expect one peak here, but I would also expect another peak here, right? To show that there's two different environments that both resolve or both sort of indicate that there's a carboxyl group. All right. Proline, on the other hand, only has one carboxyl group, which is why I am inclined to say it's proline as opposed to glutamic acid. Okay. So the reason why glutamic acid is not it is because there's two COH groups. And they should have provided some indication that there's two environments around this area that indicate the carboxyl groups. And obviously, valine and aspartic acid didn't have the right amount of environment. So that is that. I would say that it wasn't the hardest multiple choice questions that I've ever done. However, there were a couple sneaky ones in there. This one I'm gonna have to double check with some people, but I think the majority of them, like, yeah, there were, this is not for me to be like, yeah, everything here is right. I think, yeah, a lot of it is going to need fact checking, but hopefully this gives you a frame to work off with. So yeah, hope you guys enjoyed the video, and I'll see you next time.